In astronomy, the geocentric model is a description of the cosmos where Earth is at the orbital center of all celestial bodies. This model served as the predominant cosmological system in many ancient civilizations such as ancient Greece, including the noteworthy systems of Aristotle and Ptolemy. As such, they believed that the sun, moon, stars, and naked-eye planets circled Earth. Two commonly made observations supported the idea that Earth was the center of the universe. The stars, the sun, and planets appear to revolve around Earth each day, making Earth the center of that system. The stars were thought to be on a celestial sphere, with the Earth at its center, that rotated each day, using a line through the North and South Pole as an axis. The stars closest to the equator appeared to rise and fall the greatest distance, but each star circled back to its rising point each day. The second observation supporting the geocentric model was that the Earth does not seem to move from the perspective of an earthbound observer, and that it is solid, stable, and unmoving. Ancient Roman and medieval philosophers usually combined the geocentric model with a spherical Earth. It is not the same as the older flat Earth model implied in some mythology, as was the case with the biblical and post-biblical Latin cosmology. The ancient Jewish Babylonian uranography pictured a flat Earth with a dome-shaped rigid canopy named firmament placed over it. However, the ancient Greeks believed that the motions of the planets were circular and not elliptical, a view that was not challenged in Western culture until the 17th century through the synthesis of theories by Copernicus and Kepler. The astronomical predictions of Ptolemy's geocentric model were used to prepare astrological and astronomical charts for over 1500 years. The geocentric model held sway into the early modern age, but from the late 16th century onward was gradually superseded by the heliocentric model of Copernicus, Galileo and Kepler. There was much resistance to the transition between these two theories. Christian theologians were reluctant to reject a theory that agreed with Bible passages. Others felt a new, unknown theory could not subvert an accepted consensus for geocentrism. Ancient Greece. The geocentric model entered Greek astronomy and philosophy at an early point. It can be found in pre-Socratic philosophy. In the 6th century BC, Anaximander proposed a cosmology with the Earth shaped like a section of a pillar, held aloft at the center of everything. The sun, moon, and planets were holes in invisible wheels surrounding the Earth. Through the holes, humans could see concealed fire. About the same time, the Pythagoreans thought that the Earth was a sphere, but not at the center. They believed that it was in motion around an unseen fire. Later these views were combined, so most educated Greeks from the 4th century BC on thought that the Earth was a sphere at the center of the universe. In the 4th century BC, two influential Greek philosophers, Plato and his student Aristotle, wrote works based on the geocentric model. According to Plato, the Earth was a sphere, stationary at the center of the universe. The stars and planets were carried around the Earth on spheres or circles, arranged in the order: Moon, Sun, Venus, Mercury, Mars, Jupiter, Saturn. Fixed stars, with the fixed stars located on the celestial sphere. In his Myth of a section of the Republic, Plato describes the cosmos as the spindle of necessity, attended by the sirens and turned by the three fates. Eudoxus of Cnidus, who worked with Plato, developed a less mythical, more mathematical explanation of the planet's motion based on Plato's dictum, stating that all phenomena in the heavens can be explained with uniform, circular motion. Aristotle elaborated on Eudoxus' system. In the fully developed Aristotelian system, the spherical Earth is at the center of the universe, and all other heavenly bodies are attached to 47 to 55 transparent concentric spheres which rotate around the Earth. These spheres, known as crystalline spheres, all moved at different uniform speeds to create the rotation of bodies around the Earth. They were composed of an incorruptible substance called ether. Aristotle believed that the Moon was in the innermost sphere and therefore touches the realm of Earth. causing the dark spots and the ability to go through lunar phases. He further described his system by explaining the natural tendencies of the terrestrial elements: earth, water, fire, air, as well as celestial ether. His system held that Earth was the heaviest element, with the strongest movement towards the center. Thus water formed a layer surrounding the sphere of Earth. The tendency of air and fire, on the other hand, was to move upwards, away from the center, with fire being lighter than air. Beyond the layer of fire, were the solid spheres of ether in which the celestial bodies were embedded. They, themselves, were also entirely composed of ether. Adherence to the geocentric model stemmed largely from several important observations. First of all, if the Earth did move, then one ought to be able to observe the shifting of the fixed stars due to stellar parallax. In short, if the Earth was moving, the shapes of the constellations should change considerably over the course of a year. If they did not appear to move, the stars are either much farther away than the Sun and the planets than previously conceived, making their motion undetectable, or in reality they are not moving at all, because the stars were actually much further away than Greek astronomers postulated. Stellar parallax was not detected until the 19th century. Therefore, the Greeks chose the simpler of the two explanations. The lack of any observable parallax was considered a fatal flaw in any non-geocentric theory. Another observation used in favor of the geocentric model at the time was the apparent consistency of Venus's luminosity, which implies that it is usually about the same distance from Earth, which in turn is more consistent with geocentrism than heliocentrism. In reality, that is because the loss of light caused by Venus's phases compensates for the increase in apparent size caused by its varying distance from Earth. Objectors to heliocentrism noted that terrestrial bodies naturally tend to come to rest as near as possible to the center of the Earth, further barring the opportunity to fall closer to the center. Terrestrial bodies tend not to move unless forced by an outside object, or transformed to a different element by heat or moisture. Atmospheric explanations for many phenomena were preferred because the Eudox and Aristotelian model based on perfectly concentric spheres was not intended to explain changes in the brightness of the planets due to a change in distance. Eventually, perfectly concentric spheres were abandoned as it was impossible to develop a sufficiently accurate model under that ideal. However, while providing for similar explanations, the later deferent and epicycle model was flexible enough to accommodate observations for many centuries. Ptolemaic model. Although the basic tenets of Greek geocentrism were established by the time of Aristotle, the details of his system did not become standard. The Ptolemaic system, developed by the Hellenistic astronomer Claudius Ptolemaeus in the 2nd century AD, finally standardized geocentrism. His main astronomical work, the Almagest, was the culmination of centuries of work by Hellenic, Hellenistic and Babylonian astronomers. For over a millennium, European and Islamic astronomers assumed it was the correct cosmological model. Because of its influence, people sometimes wrongly think the Ptolemaic system is identical with the geocentric model. Ptolemy argued that the Earth was in the center of the universe, from the simple observation that half the stars were above the horizon and half were below the horizon at any time, and the assumption that the stars were all at some modest distance from the center of the universe. If the Earth was substantially displaced from the center, this division into visible and invisible stars would not be equal. Ptolemaic system. In the Ptolemaic system, each planet is moved by a system of two spheres. One called its deferent, the other, its epicycle. The deferent is a circle whose center point, called the eccentric and marked in the diagram with an X, is removed from the Earth. The original purpose of the eccentric was to account for the differences of the lengths of the seasons, by placing the Earth away from the center of rotation of the rest of the universe. Another sphere, the epicycle, is embedded inside the deferent sphere and is represented by the smaller dotted line to the right. A given planet then moves around the epicycle. At the same time, the epicycle moves along the path marked by the deferent. These combined movements cause the given planet to move closer to and further away from the Earth at different points in its orbit, and explained the observation that planets slowed down, stopped, and moved backward in retrograde motion, and then again reversed to resume normal, or prograde, motion. The deferent and epicycle model had been used by Greek astronomers for centuries along with the idea of the eccentric, which was even older. In the illustration, the center of the deferent is not the Earth, but the spot marked X, making it eccentric, from which the spot takes its name. Unfortunately, the system that was available in Ptolemy's time did not quite match observations, even though it was considerably improved over Hipparchus's system. Most noticeably, the size of a planet's retrograde loop would be smaller, and sometimes larger, than expected, resulting in positional errors of as much as 30 degrees. To alleviate the problem, Ptolemy developed the equant. The equant was a point near the center of a planet's orbit which, if you were to stand there and watch, the center of the planet's epicycle would always appear to move at uniform speed. All other locations would see non-uniform speed, like on the Earth. By using an equant, Ptolemy claimed to keep motion which was uniform and circular, although it departed from the Platonic ideal of uniform circular motion. The resultant system, which eventually came to be widely accepted in the West, seems unwieldy to modern astronomers. Each planet required an epicycle revolving on a deferent, offset by an equant which was different for each planet. It predicted various celestial motions, including the beginning and end of retrograde motion, to within a maximum error of 10 degrees, considerably better than without the equant. The model with epicycles is in fact a very good model of an elliptical orbit with low eccentricity. The well-known ellipse shape does not appear to a noticeable extent when the eccentricity is less than 5%, but the offset distance of the center is very noticeable even with low eccentricities as possessed by the planets. To summarize, Ptolemy devised a system that was compatible with Aristotelian philosophy and managed to track actual observations and predict future movement mostly to within the limits of the next 1,000 years of observations. The observed motions and his mechanisms for explaining them include: the geocentric model was eventually replaced by the heliocentric model. The earliest heliocentric model, Copernican heliocentrism, could remove Ptolemy's epicycles because the retrograde motion could be seen to be the result of the combination of Earth and planet movement in speeds. Copernicus felt strongly that equants were a violation of Aristotelian purity, and proved that replacement of the equant with a pair of new epicycles was entirely equivalent. Astronomers often continued using the equants instead of the epicycles because the former was easier to calculate, and gave the same result. It has been determined, in fact, that the Copernican, Ptolemaic and even the Tychonic models provided identical results to identical inputs. They are computationally equivalent. It wasn't until Kepler demonstrated a physical observation that could show that the physical sun is directly involved in determining an orbit that a new model was required. The Ptolemaic order of spheres from Earth outward is Moon, Mercury, Venus, Sun, Mars, Jupiter, Saturn, fixed stars, primum mobile. Ptolemy did not invent or work out this order, which aligns with the ancient seven heavens religious cosmology common to the major Eurasian religious traditions. It also follows the decreasing orbital periods of the Moon, Sun, planets and stars. Geocentrism and Islamic astronomy. Muslim astronomers accepted the Ptolemaic system and the geocentric model, but by the 10th century texts appeared regularly whose subject matter was doubts concerning Ptolemy. Several Muslim scholars questioned the Earth's apparent immobility and centrality within the universe. Some Muslim astronomers believed that the Earth rotates around its axis, such as Abu Sa'id al-Sijzi. According to al-Biruni, Sijzi invented an astrolabe called al-Zuraki based on a belief held by some of his contemporaries, that the motion we see is due to the Earth's movement and not to that of the sky. The prevalence of this view is further confirmed by a reference from the 13th century which states, according to the geometers, or engineers, the Earth is in constant circular motion, and what appears to be the motion of the heavens is actually due to the motion of the Earth and not the stars. Early in the 11th century, Alhazen wrote a scathing critique of Ptolemy's model in his Doubts on Ptolemy, which some have interpreted to imply he was criticizing Ptolemy's geocentrism, but most agree that he was actually criticizing the details of Ptolemy's model rather than his geocentrism. In the 12th century, Aristotelian departed from the ancient Greek idea of uniform circular motions by hypothesizing that the planet Mercury moves in an elliptic orbit, while Alpetragius proposed a planetary model that abandoned the equant, epicycle and eccentric mechanisms, though this resulted in a system that was mathematically less accurate. Fakhr al-Din al-Razi, in dealing with his conception of physics and the physical world in his Matalib, rejects the Aristotelian and Avicennian notion of the Earth's centrality within the universe, but instead argues that there are 1,000 worlds beyond this world such that each one of those worlds be bigger and more massive than this world, as well as having the like of what this world has, to support his theological argument. He cites the Quranic verse, "All praise belongs to God, Lord of the worlds," emphasizing the term worlds. The Maraha revolution refers to the Maraha school's revolution against Ptolemaic astronomy. The Maraha school was an astronomical tradition beginning in the Maraha Observatory and continuing with astronomers from the Damascus Mosque and Samarkand Observatory. Like their Andalusian predecessors, the Maraha astronomers attempted to solve the equant problem and produce alternative configurations to the Ptolemaic model without abandoning geocentrism. They were more successful than their Andalusian predecessors in producing non-Ptolemaic configurations which eliminated the equant and eccentrics, were more accurate than the Ptolemaic model in numerically predicting planetary positions, and were in better agreement with empirical observations. The most important of the Maraha astronomers included Mu'ayyad-ud-Din Urdi, Nasir al-Din al-Tusi, Qutb al-Din al-Shirazi, Ibn al-Shatai, Ali Quja, al-Burjandi, and Shams al-Din al-Khafray. Ibn al-Shatai, the Damascene astronomer working at the Umayyad Mosque, wrote a major book entitled Kitab Nihayat al-Sulfi Tashi al-Usul on a theory which departs largely from the Ptolemaic system known at that time. In his book, Ibn al-Shatai, an Arab astronomer of the 14th century, Kennedy wrote, "What is of most interest, however, is that Ibn al-Shatir's lunar theory, except for trivial differences in parameters, is identical with that of Copernicus. The discovery that the models of Ibn al-Shatir are mathematically identical to those of Copernicus suggests the possible transmission of these models to Europe. At the Maraha and Samarkand observatories, the Earth's rotation was discussed by al-Tusi and Ali Quja. The arguments and evidence they used resemble those used by Copernicus to support the Earth's motion. However, the Maraha school never made the paradigm shift to heliocentrism. The influence of the Maraha school on Copernicus remains speculative, since there is no documentary evidence to prove it. The possibility that Copernicus independently developed the Tusi couple remains open, since no researcher has yet demonstrated that he knew about Tusi's work or that of the Maraha school.